Metal spinning is where true craftsmanship intersects with the art of restoration, and few examples embody this as beautifully as crafting an aluminium nose cone for the legendary Spitfire. This meticulous process begins with a 3 mm thick aluminium blank, a simple disc destined to become a precision aerospace component. For production methods, this work embraces tradition and skill. The aluminium disc is mounted onto a spinning chuck, but instead of expensive metal dies, a wooden former shapes the piece. A practical and cost-effective choice for low-volume, custom parts like those required in vintage aircraft restoration. As the lathe spins, the shop hums with the rhythmic whirl of machinery and the scraping sound of metal forming against wood. A skilled operator, armed with handheld forming tools, steadily presses the aluminium into the wooden mold. Each pass smooths the surface, coaxing the edge to curl inward, wave-like, under controlled pressure. No two sessions are ever identical. There's constant fine-tuning, a subtle adjustment of wrist angle, a shift in pressure, all guided by the operator's eyes and years of experience. There's no computer screen tracking progress. The craftsman judges every curve, arc, and thickness in real time. The shaping is gradual, as the aluminium work hardens, stretching and thinning into a flawless, curved surface without removing any material. Precision is paramount. Too much force and the metal risks tearing. Too little, and it won't form correctly. Once the desired shape is achieved, the nose cone is carefully trimmed from the remaining blank. Edges are cleaned, and the surface inspected for uniformity. The result is a unique, aerospace-grade component, crafted entirely by hand, preserving both function and historical authenticity. Metal spinning for Spitfire nose cones is not about speed, but about mastery and control. Molding involves packing sand tightly around the pattern to form a cavity replicating the component's shape. The sand mixture often includes binders for strength and precision. Cores may be inserted to create internal passages. Molds are then assembled, vented, and prepared to receive molten metal during pouring. In melting and pouring, metal is heated in furnaces until molten, then carefully poured into prepared molds. Temperature control ensures proper flow, preventing defects and achieving desired mechanical properties. After cooling, the casting proceeds to shake out, where the sand mold is broken away, revealing the rough casting. Finally, in finishing, workers remove excess material, smooth surfaces, and inspect the casting for defects. Each step in foundry casting is crucial for producing robust, high-performance components used in industries like mining, construction, and heavy machinery. At FBF Professional Hand Tools, crafting begins with coiled lengths of high-grade steel wire. This wire is systematically fed into cutting machines, slicing out uniform blanks for the handles and jaws with crisp, exact cuts. Next comes forging, a stage where intense heat and powerful hammers shape the steel into the distinctive geometry of plier jaws. This forging ensures the jaws will grip electrical connectors with perfect alignment and strength. Heat treatment then transforms the forged steel into a tool ready to endure tough use. The plier components undergo controlled quenching and tempering cycles, which enhance the steel's strength and resilience. Surface scale, a byproduct of heating, is meticulously removed using abrasive belts, revealing clean, flawless steel underneath. Precision machining comes into play as CNC machines drill and ream pivot holes with micron-level accuracy. The plier handles are then fitted with insulated grips designed to withstand voltages up to 1,000 volts. These grips undergo rigorous testing, including immersion in water baths while exposed to high voltages, ensuring they provide the necessary protection and safety. Before moving into assembly, the parts are thoroughly blasted and degreased. Cleanliness is non-negotiable because any residual contamination could affect insulation integrity or mechanical fit. Even the slightest misalignment or residue could mean potential failure in the field, an unacceptable risk in electrical work, where tolerances are measured in fractions of a millimeter. Bar shearing precisely cuts raw material bars to required lengths. Friction welding is a solid-state joining process used to fuse engine valve components without melting. It generates heat through mechanical friction between the parts, followed by axial pressure to create a strong, high-integrity. This method ensures consistent quality, excellent strength, and minimal distortion, making it ideal for critical applications like valve stem-to-head assembly in automotive engines. Upset forging is a key process in manufacturing engine valves, where a heated metal bar is compressed axially to increase its diameter and form features like valve heads. This technique improves the material's grain flow, enhancing strength and fatigue resistance. It ensures precise dimensional control and efficient material usage. In valve production, upset forging provides the foundation for durability and reliable performance under high temperatures and mechanical stress in engine environments. Heat treatment in a continuous furnace uniformly heats engine valves to precise temperatures, enhancing hardness, strength, and wear resistance, ensuring durability and consistent mechanical properties for demanding engine applications. Seat grinding precisely shapes valve seating surfaces, ensuring proper sealing, optimal airflow, and reliable engine performance under high-pressure conditions. Auto-loading by bowl feeder for machining line. Profile turning forms valve contours for accurate engine fit. Groove grinding creates precise stem grooves for secure valve assembly. Turn head dia and facing involves machining the valve head's diameter and front surface to precise dimensions. This ensures proper sealing, balanced rotation, and optimal fit within the engine's combustion chamber. Induction hardening end strengthens valve tip for wear resistance. Finish end grinding ensures smooth, precise valve tip dimensions. Seat grinding finishes the valve seat surface precisely, ensuring perfect sealing, optimal combustion efficiency, and extended valve life in engine operations. Induction hardening of the valve seat uses localized electromagnetic heating, followed by rapid quenching to harden the surface. This enhances wear resistance, strength, and fatigue life, ensuring the valve seat withstands high temperatures and pressures in engine environments. Chrome flat plating deposits a thin layer of chromium onto the valve stem surface. This improves wear resistance, reduces friction, and enhances corrosion protection, ensuring smoother valve operation and extended lifespan. The process also provides a consistent surface finish, crucial for maintaining precise clearances and reducing engine component wear. Smelting is the critical stage in metal casting, where raw metal is heated until it becomes a molten liquid, ready to be poured into molds. The process typically begins with selecting appropriate metal ingots or scrap, such as stainless steel, copper alloys, or aluminum, based on the part's required properties. These metals are placed in a crucible, often made of graphite or ceramic, and heated using induction furnaces or flame-based systems. Induction furnaces use electromagnetic fields to generate heat efficiently, allowing for precise temperature control, while flame furnaces rely on gas or oil combustion. During smelting, impurities or slag may rise to the surface and are removed manually to ensure metal purity. Skilled workers monitor the process visually, judging the metal's glow and fluidity to determine readiness. Next comes the critical step of creating a ceramic shell around the wax assembly. The wax tree is dipped into a slurry made of colloidal silica mixed with fine refractory powders such as zircon. Excess slurry is drained, and the assembly is coated with layers of fine and coarse sand. This dipping and coating process is repeated multiple times to build a robust ceramic shell of the required thickness. Each layer must dry completely before the next is applied, ensuring a shell strong enough to withstand the pressure of molten metal during pouring. Once the ceramic shell is complete, the wax is removed through a process called de-waxing. The assembly is placed in a high-pressure steam autoclave or heated in a furnace, melting and draining the wax from the mold. Following de-waxing, the ceramic shell undergoes high-temperature sintering, 700 to 1,100 degrees Celsius, which burns out any remaining wax residues and significantly increases the mold's strength. The castings are separated from the sprue tree, excess metal is trimmed off, and surfaces are cleaned via sandblasting or manual polishing. Additional machining is minimal, typically reserved for functional surfaces like threads or mating faces. Material inspection checks steel's chemical composition, mechanical properties, surface defects, and dimensions, ensuring only quality materials proceed to production. In tube cutting, long steel tubes are measured and precisely cut to required axle lengths using automatic cutting machines or saws. Accurate cutting is essential to maintain consistent axle dimensions and reduce waste. After cutting, ends are deburred to remove sharp edges, ensuring safe handling and proper fit in subsequent processes. Quality checks verify cut length tolerances and surface condition, laying a solid foundation for downstream forming and machining operations. Hot rolling in axle manufacturing shapes the axle tube ends into specific profiles required for spindles or axle necks. The process begins by heating the tube ends to high temperatures, typically between 1,100 degrees Celsius and 1,250 degrees Celsius, making the steel malleable. Once heated, hydraulic or mechanical rolling machines apply controlled pressure, gradually deforming the tube ends into the desired geometry. This operation not only shapes the axle ends, but also refines the steel's grain structure, enhancing mechanical properties like strength and toughness. Careful temperature control is crucial to prevent overheating, which could cause grain coarsening or surface defects. After rolling, the parts are allowed to cool under controlled conditions to minimize residual stresses. Dimensional checks follow to ensure precise measurements and concentricity. Hot rolling is vital because it provides the correct spindle profile, essential for bearing fits and load-bearing performance. It also reduces material defects and sets the stage for subsequent machining and heat treatment processes. Two-end cutting, often called end facing, involves machining both ends of the axle tube to achieve precise length and smooth, perpendicular surfaces. Specialized facing machines or lathes trim the ends to exact specifications, removing any irregularities left from previous cutting or rolling. This ensures the axle's overall length tolerance and creates flat surfaces necessary for accurate alignment in later processes. Proper end cutting is critical for achieving concentricity, preventing assembly issues, and ensuring balanced rotation during axle operation. The square beam pushing process uses hydraulic presses to reshape round axle tubes into square or rectangular cross-sections required for specific axle designs. Controlled pressure uniformly pushes the steel into precise die molds, ensuring consistent dimensions and wall thickness. This process improves axle strength and load distribution, preparing the beam for subsequent heat treatment and machining operations while maintaining structural integrity. Heat treatment, also called hot treatment, is a crucial step that improves the axle's mechanical properties, durability, and performance. During this process, axle beams are heated in large furnaces to temperatures typically ranging from 850 degrees Celsius to 950 degrees Celsius, depending on the steel grade and desired properties. The heating stage relieves internal stresses from previous forming operations and refines the steel's grain structure. Once at the target temperature, the axles undergo controlled cooling, either rapid quenching in oil, water, or air, or slower cooling for processes like normalizing or annealing. Quenching increases hardness and strength, but may introduce stresses, which are reduced through tempering, reheating the steel to moderate temperatures to improve toughness and ductility. Precise temperature and time controls ensure uniform properties throughout the axle. Post-treatment inspections check hardness, microstructure, and dimensions. This step is vital because it gives the axle the strength and fatigue resistance needed to endure the heavy loads and demanding conditions of trailer operation. Shot blasting is a mechanical surface cleaning process where high-speed steel shots or grit bombard the axle's surface, effectively removing mill-scale, rust, oxide layers, and heat treatment discoloration. The axle is placed in a blasting machine, where rotating turbines propel abrasive media under controlled pressure and speed. This not only cleans the surface, but also creates a uniform, slightly rough texture enhancing paint adhesion in later processes. Additionally, shot blasting induces compressive stresses on the axle surface, improving fatigue strength and resistance to cracking under dynamic loads. Thorough coverage is crucial to avoid untreated spots that could compromise corrosion protection or coating quality. After blasting, axles are inspected for surface cleanliness and finish, ensuring readiness for subsequent machining, painting, or coating processes. Straightening corrects any bending or deformation that occurs during earlier processes like rolling, heat treatment, or cooling. The axle is placed into a hydraulic or mechanical straightening machine, where precise pressure is applied at calculated points along its length. Skilled operators or automated systems measure runout and adjust the force to ensure perfect alignment. Accurate straightening is essential for axle performance, as even slight bends can cause vibrations, uneven tire wear, and premature bearing or suspension failures in service. Hole boring and end scraping refine the inner diameter and end surfaces of the axle tube. Boring machines precisely enlarge and smooth internal holes to exact tolerances, ensuring proper fit for spindles or bushings. End scraping removes residual burrs and imperfections, creating smooth surfaces. This process guarantees dimensional accuracy, concentricity, and reliable assembly in later manufacturing steps. Fine machining uses precision lathes, milling machines, and CNC equipment to achieve tight dimensional tolerances and smooth surface finishes on critical axle areas, such as bearing seats and spindle profiles. This step ensures exact fits for components like hubs and bearings, reduces friction, and enhances load distribution. Precise machining is essential for axle performance, longevity, and safe vehicle operation. In hole drilling and keyway milling, specialized machines create precise holes for mounting bolts, brake components, or lubrication channels, ensuring exact placement and dimensions. Keyway milling cuts narrow slots along the axle shaft, enabling secure connections with hubs or gears. Accurate drilling and milling are vital for proper assembly, torque transmission, and maintaining axle alignment and operational safety. Medium-frequency quenching is an induction hardening process used to increase surface hardness and wear resistance on critical axle areas like bearing seats and spindles. An induction coil generates an alternating magnetic field at medium frequencies, typically 1 to 10 kHz, rapidly heating the steel surface to temperatures around 850 to 950 degrees Celsius, while leaving the core cooler and tough. Once heated, the surface is immediately quenched using water or polymer solutions, transforming the steel's microstructure into hard martensite. This localized hardening enhances fatigue resistance and extends axle life under heavy loads and frictional stresses, without compromising the axle's core toughness. Precise control of power, heating time, and quenching ensures uniform hardness and avoids defects like cracking or distortion. After quenching, hardness testing verifies that the desired properties have been achieved, ensuring the axle can withstand demanding operational conditions. Outer circle grinding uses high-precision cylindrical grinding machines to finish critical external surfaces of the axle, such as bearing journals and spindle shafts. This process removes minimal material to achieve exact diameters, tight tolerances, and superior surface finishes, often in the micron range. Precision grinding ensures proper fit, smooth rotation, reduced friction, and reliable performance during axle operation and vehicle use. Bushing installation involves pressing durable metal or composite bushings into axle ends, ensuring precise fits, smooth rotation, and wear resistance. Brake bracket welding attaches steel brackets onto the axle beam, providing secure mounting points for brake chambers and related components. Skilled welders or automated robotic systems precisely position and weld the brackets using MIG or submerged arc welding techniques. High-quality welds ensure structural integrity, alignment accuracy, and resistance to stress during braking forces. Post-welding inspections, including visual checks and sometimes non-destructive testing, confirm weld strength and quality. Properly welded brackets are crucial for safe and effective braking performance in trailer operation. Six-hole boring precisely drills a set of 6 evenly spaced holes into the axle ends, typically used for mounting wheel hubs, brake components, or flanges. CNC or specialized boring machines ensure exact positioning, consistent diameters, and perfect symmetry. Accurate 6-hole patterns are critical for balanced wheel assembly, secure fastening, and smooth rotation, preventing vibrations and ensuring safe, reliable axle performance. Camshaft installation involves fitting the camshaft through bushings inside the axle housing. The camshaft connects to brake components, translating rotational force into linear motion to operate brake shoes. Precise alignment and secure fastening ensure smooth movement and reliable braking response. Technicians check for correct end play, smooth rotation, and proper engagement, as camshaft function is vital for safe trailer braking performance. Painting protects the axle from corrosion and enhances its appearance. Axles are cleaned and passed through an automatic painting line, where they receive primer and topcoat layers, often applied via electrostatic spraying for uniform coverage. The paint cures in controlled ovens to achieve a durable, chip-resistant finish. Paint thickness and adhesion are checked to meet quality standards. Effective painting not only prolongs the axle's service life under harsh environmental conditions, but also contributes to a professional, branded product appearance.